Thank you very much, and welcome to my presentation today. This is my first time at PyCon, and it's also my first time in Cardiff, and I like both very much. So, welcome to the presentation today of our work on Adversarial Robustness Toolbox. It's an open source project that we developed at IBM Research. Oh, I have to say I'm from the Dublin Research Laboratory of IBM Research, and there we have developed in the last 1.5 years Adversarial Robustness Toolbox, which we abbreviate as ART. It's on GitHub. There's an MIT license, so everybody can have a look and use and extend it. Let me first introduce to you what are adversarial threats to machine learning. Now, in the past 2 days, I've seen several talks that have been talking about how to do machine learning correctly, how to select the proper model, how to do cross-validation correctly, so that you really get a good machine learning model that has good prediction accuracy. Now, this talk is about what can go wrong, even if you have done everything right. How can everything go completely wrong suddenly without you doing anything? But now, this is the adversarial threat. What we have here is a typical machine learning pipeline. So we have the data that we use to train a machine learning model. We have our machine learning model, maybe a neural network, but it can also be any other type of machine learning model. And we would like to use it to take input and create output in form of a prediction. Now, an adversary or an attacker has two main attack routes to attack a machine learning model. So there are first evasion attacks. They are performed at test time by perturbing the input features with craft noise that is ideally undetectable by humans to fool the model to make a wrong prediction. And if possible, even the prediction chosen by the attacker. So that's the red attack route here, where we go and modify the input to the machine learning model. Then, as a second attack route, there are also poisoning attacks, where before even the machine learning model is trained, the attacker tries to poison the training data by introducing a poison in form, let's say, if the training data are images, then there could be certain image pixel pattern that the machine learning model then associates very closely with a certain label, and that pattern can then, which is only known to the attacker, can be exploited later on by adding it to the input to change the behavior of the machine learning models through a backdoor kind of attack. Now, does this happen in the real world? It's kind of starting. People start to talk about it. What I've shown here is a recent it's a picture from an article in Science magazine about the policy forum, and it's adversarial attacks in medical machine learning is the topic. So it lists possible ways of doing such attacks in deployed models in medical machine learning. So for example, the first row here shows an image of skin cancer, and you would have a machine learning model that classifies this as cancer or not. And the adversarial noise would be something like this. It would be specially crafted by a mathematical operation, and it would be added to the pixel values. And as you see, the resulting image, a human doesn't recognize that the noise has been added. But what happens is that the classifier, who initially classified it as benign, classifies this now as malignant skin cancer. So that's one form of attack, and it's very clearly to see how there's a malicious intent behind this kind of behavior if you add especially crafted noise to an image. Now, the ethical gray zone starts with other types of attacks. People have shown that you can rotate the image, for example, of the skin cancer image, and you can rotate it as long as you need, and at some point you might find the rotation angle where the classification of that image changes. And then you can submit this rotated image to the, for example, website of your insurer, and you get classified as being eligible for insurance payout. Now here, it's more difficult to define where criminal behavior starts, because there's no rule against rotating images. Similar attacks have been demonstrated on text. So for example, in this case, there would be that, for example, a text classifier, the idea would be if you would use more negative terms to describe a disease or a condition of a patient, that it would classify it as a high opioid abuse risk, whereas if you would use more positive or more technical terms in the description, that it might lead the classifier to a more positive classification of the opioid abuse risk. And similar things have been demonstrated for machine learning in adversarial coding or coding of your insurance claim, in that different possible combinations of insurance claims can lead to different classifications of your insurance case. There's also been very recently, art has been mentioned in a vulnerability note by the Carnegie Mellon University Coordination Center. There has been the Silence antivirus product has been using a neural network that uses features of binaries to classify them as viruses or not. And there has been kind of an evasion attack going on there, that the attackers have found out which kind of features Silence is using, and then just exhibit these features in their malicious software. So this kind of a very high-level architecture diagram of Adversarial Robustness Toolbox. So it's a Python library, and we are supporting most of the neural network libraries like TensorFlow, PyTorch, Keras, MXNet. But recently we did a lot of work to also support the more classical machine learning models. For example, especially the ones from scikit-learn, and also like GBM, CatBoost, and XGBoost models. So this gives you also the possibility to use art with logistic regression, support vector machines, decision trees, and so on. Now, art is not just about attacking models, it's also about protecting machine learning models. So art provides different measures to protect your model. So you have your conventionally trained unsecure model here in the red box that tries to classify images into labels. And so the three main steps to protect your model are by adversarially retraining it. That is very effective for neural networks. Then we have a large group of input pre-processing methods that kind of slightly modify your input image to try to remove adversarial features. And then we also have output post-processing layers that often try to do non-differential modification of the predicted output to increase the robustness and also even to increase the theft of the model. So because it's a toolbox, I have here the full list of tools that the toolbox provides. It has a lot of evasion attacks. These are the ones that we discussed before, but there are also poisoning attacks. We have one specifically for the support vector machines. Then we have a longer list of defenses, so mostly in input processing defenses. Then we also have a large group of robustness metrics. So these are, when you have a model, you can run these robustness metrics and it will give you an idea how robust the model is against adversarial attacks. And then we also have detection methods. So we can detect adversarial samples in the inputs by running detectors on inputs, but also by running detectors on activations of neural networks. And then we also have detectors for poisoning attacks, which mainly run an analysis of the activations of a neural network. So on the next 3 slides, I would like to run you through kind of an adaptive attack on a very simple model, with a very simple attack. So that's the fast gradient sign method. It's basically, I say it's a simple attack because it just requires you to calculate the gradients with respect to the input ones. And then you use these gradients to modify the input image, and then that is your adversarial sample. And what I'm showing here is kind of a minimal example of the code that is required to create such an example with R.
The code is not quite clear. Is there any chance?
I'm not sure if I can zoom in very nicely.
Maybe just background. Can you highlight it with your cursor?
Oh, yeah.
Can you try slightly better?
I think the light is very bright here,
Right.
but I can show you the slides afterwards. So basically what we have is we load an image at the beginning, then we load the model. Here, in that case, it's a Keras model from an H5 file. And then we have a class, for example, a Keras classifier, which is provided by R, and it takes the model as input and some information about the images. So this is the pixel value, the pixel range. It goes from 0 to 255 in this case. And so we create this instance of a classifier. Then in this line, we create an attacker, which is with the fast gradient method class that R provides. And it takes, its main argument is epsilon, which defines the attack strength of this attack. So this means in this case, the attack can change each pixel by a maximum of ±2. And then we call it the generate function on that image, and it creates us an adversarial image. And in the last line, we evaluate the classifier on that image. Now, what we see is that on the original image, this Siamese cat picture is classified with a probability of 92% as a Siamese cat. And the adversarial image with the same neural network is predicted as an Egyptian cat with 30%. So this shows that that's why this is a simple and weak attack, because it's still a cat, but it's a different kind of cat with less certainty. So it's somehow successful, this attack. Now, what we can do about it is we add in this line one of the defenses, in this case spatial smoothing. So that's doing spatial smoothing of the image before it's fed into the classifier. And here with a window size of 5, we see that the classification goes back to Siamese cat with a somewhat lower probability, but still the correction goes correctly. Now, if the attacker noticed that, the attacker has then also the possibility to adapt to these defenses and increase the attack strength. So in this slide, we increase the epsilon of the attack from 2 to 8. And we see that we can then again fool the classifier into believing this is an Egyptian cat with quite high probability that this is an Egyptian cat. But what you can see also here is that the image is now much more blurred. I'm not sure if with the light if it's visible, but the image is now much more a little bit blurred because of this spatial smoothing step. Now, there are also much more stronger attack and more elaborate attacks. So for example, the Kalinin-Wagner attack, I would label that as a strong attack. The code is very similar as to the code before. We just use a different attack method provided by R. And because it's a little bit more elaborate, it also takes much more parameters as input, but they are nice, they are well documented in the documentation. But what we also can show, previously that was an untargeted attack. We just wanted to change the picture so that the classifier predicts the wrong model. Now here we can afford to do a targeted attack so that the image is changed to make a prediction of a specific class. So because this is an ImageNet classifier, we have chosen here class 407, which is an ambulance. And so we tell the attack that we created that we would like to create an adversarial image that is classified as an ambulance. And this is still the original image of the Siamese cat, and the adversarial image that we create with this strong Kalinin-Wagner attack is now then classified with very high probability as an ambulance. And you see there's minimal distortion between the adversarial image and the original image. And this is what a strong adversarial evasion attack can do. Now, as the last example, I would also like to show that we have a lot of black box attacks. So black box attacks means that you only need the output of the classifier to create your adversarial sample. Instead of as before, you need the weights and the model structure to calculate the gradients. Here you only need the actual output. And what we are showing here is an adversarial attack on Tesseract, the optical character recognition engine. And we have two images of two words. We have descent and ascent. If we feed these images to Tesseract, we get correct classifications as descent and ascent. So we can use the hop, skip, jump attack implemented in R, which modifies the ascent image to this image. And if you would look like it, you can clearly see it shows the word descent. So you can recognize there's some noise around it, but this end is clearly visible. If you feed that into tesseract, it will return to you ascent, which is the wrong word for that image. So on the last slide, I have here a summary of the resources. So we are in GitHub. You can look at the code and use it for your project. We also have documentation on Read the Docs. We have a Slack channel, and on the README on GitHub, there's an invitation if you would like to join. We have a live demo, and we also have a blog article describing the new features of our recent major release. And as the very last slide, ART is part of IBM Research's Trusting AI initiative, and as part of that, we have recently also released the AI Fairness Toolkit, which is a similar toolkit for methods to ensure fairness in machine learning, and also AI Explainability Toolkit, which helps you make your machine learning models explainable. Thank you very much.
Thank you very much for a very interesting talk. Does anyone have any questions?
So you said you can create a secure model with pre-processing and then output processing as well. Does that lead to a decrease in accuracy if you were to rerun it on your original data set?
Yeah, it's I didn't say it makes a completely secure model, because it's always an adaptation of the attacks. But there's a trade-off between accuracy on benign samples and accuracy on adversarial samples. So to bring the accuracy on adversarial samples higher, you have to sacrifice a little bit on the benign samples. But that's where the ongoing research is, that you can keep your benign accuracy while still having reasonable adversarial accuracy.
Thank you for the talk. It's very interesting. It might be a coincidence, or maybe because it's most the easiest way to visualize it. But all the examples, they, as far as if I'm not mistaken, they were with images. So we apply some filters to images in order to trick the system. So is it possible to use the same toolbox for some highly customized, tailored data sets? Say if we use our own data set, which is highly processed, it doesn't resemble anything from the nature world. It's just long metrics of it's carefully crafted. But still, if we apply some kind of attack to the data set, obviously we might trick our system as well. But would all these techniques work out of the box on a custom data set? Probably not. So how you would handle that? Or is it only for images? Or
yeah, I forgot actually to mention that. It's a good point. The reason why the library started with images, and we use images because they make nice visualizations. But for the recent major release that we published, we extended to work with any kind of data. So you can use tabular data from your database or any input shape map. It's not that every method will work with tabular data, so some of the methods specifically expect three-dimensional image tensors, but most of the methods should work with tabular data.
Thanks for the talk. It's more of a speculative question, like in a business environment where you usually use your data to train models and then your data to predict the models. Where do you think is like the biggest danger of adversarial attacks?
It has been demonstrated that there's this, let's say, paper that got a lot of publicity was that you have your stop sign, and then there were people putting some stickers on that stop sign in a special way, or made the sticker with showing a certain pattern, that it then fooled the software that is used by many self-driving cars not to recognize it as a stop sign anymore. So let's say there are probably more ways to create chaos with such kind of things. Rather, I'm not sure if, yeah, I cannot speculate how you can make monetary rewards with it, But for example, if let's say our position at the moment is more to create the awareness that if you would go, if you're an insurance company and you would like to deploy your machine learning model so that people can like upload images from whatever, let's say their incident, that these images can be modified in a way to fool your machine learning model, so that there's an awareness that even if you have a very good machine learning model, things can still go wrong. That's kind of.
Can you comment on which is the best attack to use?
Oh.
Or the hardest attack to defend against?
It depends. Let's say in a white box setting, this means that you have access to the model and the weights. I would say the Carlinian Wagner is probably one of the strongest ones because it's really doing very good optimization to find really minimal distortion to work. Now, in a black box setting, hop-skip jump, I would say, is currently the leader because it needs a minimal number of requests to the model to get a successful change of the prediction. So in black box settings, the measure is how many queries you need to the model, and I think hop-skip jump is in the order of a few thousand, maybe 10,000 queries.
Sorry, another question. And how do you actually protect yourself from this kind of attack? So I can imagine that if we apply these filters to our source data set, and we see that our model cannot cope with that and the prediction is wrong, so would it be right then to inject a lot of poisonous data into our data set, but manually to classify it as Siamese cat instead of Egyptian cat? And this way we would kind of train our model to recognize that and classify it correctly. Is it the right approach at all, or is it just, or is it going to do more harm than good? Or if it's the wrong way, then how do you prevent this from happening?
It's a difficult question. That's what I would say. That's where research still tries to find out how to make completely secure machine learning models. The amount of defenses that you can afford depends on how valuable the thing is you try to protect. Because there are many steps that you can do. You can do the input pre-processing. Then you also can monitor the traffic of some user. So for example, if somebody does 10,000 queries of very similar images in a row, then you could kind of guess there's a black box attack going on. So let's say you don't want to, I'm not sure if it's possible to completely prevent it, but you want to change the behavior or the effort that an attacker has to invest in a way that you can use other methods to detect that somebody is doing something bad so that you can turn off their accounts.
If there are no further questions, let's thank Bea. So now there'll be a coffee break, but note that in the next session there's been a schedule change, so the hangar talk will actually be at 4:30 in this room. Check the schedule online, it's up to date.